Now, let's understand the differences between micro, macro, and weighted, and when can we use them, and their limitations. So, micro average, as mentioned, it calculates the matrix globally by counting the total true positives, false positive, false negative, and false positives across all of the classes, and it aggregates them without considering which class they refer to, and the micro focuses on getting the performance across all of the classes, giving equal weight to each instance, and micro, recall, is less sensitive to class imbalance or imbalanced datasets because it aggregates contributions of all classes, so we can use the micro with imbalanced datasets, but it may overlook the performance on the minority classes. So what is the meaning of balanced and imbalanced datasets? Simply, if we have a dataset with 3 classes, class A, class B, and class C, and let's say we have here 100 records for class A, 99 for class B, and 101 records for class C. And let's assume another dataset that contains also classes A, B, and C. Here we have 200 for class A, 50 for class B, and 1000 for class C. What do you think? Which is balanced and which is imbalanced? Simply, balanced dataset means that the number of records per category or per class is close to other classes. So simply, this dataset is balanced because all of the numbers or the number of records per category is close to others. But here, there is a big gap between 250 and a big gap between 50 and 1000. So this dataset is imbalanced. There are multiple techniques to convert imbalanced datasets to balanced datasets, and we are going to cover that in a later lecture. And these imbalanced datasets need a special treatment because the minority class may get ignored, and this would be reflected in the performance metrics. For example, if you are calculating the sensitivity, it may be very low, but if you are calculating the specificity, it may be very high. So in that case, the classification model may overlook the minority class. So the idea here, if you got the number of records per class is close to others, then you can call this dataset is balanced. Otherwise, it will be imbalanced. What about macro average? Macro average calculates a matrix for each class independently and then takes the average or the mean. And they are highly sensitive to class imbalance because it treats all classes equally. So you can use micro average with balanced datasets. And its limitation is that it may overemphasize the performance on minority classes. The last one is weighted average. Here we are multiplying by the weight or taking the weighted average based on the samples number in each category. And the weight here gives more importance to larger classes, so we can use it with imbalanced, and also it can be used for balanced datasets, but it may still be biased toward larger classes rather than micro average. So if we made a concise comparison, macro average is highly sensitive to imbalanced datasets, but micro and weighted are less sensitive. We can use micro and weighted for imbalanced datasets and macro for balanced datasets. And you can report the 3 metrics and compare between them. So now you understand what is the meaning of the performance metrics and the aim behind it, which is measuring the performance of the system so that we can compare between different systems together. So if you got a system with a higher accuracy, a high sensitivity, and another with a lower sensitivity and lower accuracy, then based on that performance, you will judge that the systems that got higher values will be better. Then you understand how to extract the different values from the diffusion matrix, whether you are dealing with binary classification or multi-class classification, and based on the different components, TP, TN, FP, and FN, you can calculate the different metrics. If you are dealing with binary classification, it's an easy way. Just calculate the metric, you will get a single value. And if you are dealing with multi-class classification, you will end up with number of metrics equal to the number of classes. So what is the next step is to calculate micro, macro, or weighted based on whether it's imbalanced or balanced dataset. Macro by taking the average, weighted by applying the weight, micro by aggregating all of them as a single value. You will end up with single values, you can report macro, and weighted metrics together and compare between them. After understanding how to do that and calculate and measure the performance of a system, we need to know how to pre-process the data so that we can apply it to the machine learning model and then get that performance. The first step is called label encoding, and label encoding here is a technique used to convert categorical data into numerical format by assigning a unique integer to each category. And this method is very simple and straightforward, and it's efficient for transforming categorical variables into format suitable for machine learning algorithms, which typically require numerical input. Why it's required? Simply assume that we have dataset, and the last column, which is the category or the class, will be short, medium, high, and so on. So if I asked you to calculate the performance and assume that the prediction is medium, high, medium, and so on, you will wonder how to deal with these letters or these names, because calculating the confusion matrix or the performance requires numbers, requires counting. So simply, you can convert each of these categories into numbers, and based on these numbers, we can calculate the corresponding matrix. So the idea of the conversion is to get the unique categories and give each of them a number or a value or a meaningful order. So the label encoding is very useful with ordinal categorical variables. So in our example here, short, medium, and high, they are sorted. So we can give here 0, medium 1, and high 2. The next step is scaling the features, or called features normalization. And scaling the features before applying them to a machine learning model is crucial because it ensures that all features contribute equally to the model's learning process. As we mentioned multiple times, normalization is beneficial because sometimes you can find features with high ranges, maybe between 1K to 10K, and some features between 0 and 1, and some features between -1 and 1, and so on. So scaling these features to the same range assumed between 0 and 1 will make them contribute equally, so that the model can learn to focus on discriminating between the classes themselves instead of the ranges. As many machine learning algorithms such as KNN and support vector machine and also neural networks are sensitive to the scale of the input data. So sometimes features with larger magnitudes can dominate the model's behavior, leading to bias or suboptimal results. So we need scaling so that the model can converge faster and produce more reliable and interpretable results, especially, as mentioned, when you are dealing with datasets containing features of varying units or ranges. So there are different techniques for normalization. The first is called standardization. And the standardization here is to apply standardization to the features by simply removing the mean and scaling to the unit variance. And this will assume the data to follow a Gaussian distribution. And the output features or the scaled feature vector will have a mean of 0 and a standard deviation of 1. So how to do that? Simply subtract by the mean, and here this is the mean value of the feature, and divide by the standard deviation of the feature. The second method is called min-max scaling, and here we are translating each feature individually, such as the given range on that vector is between 0 and 1. And here we don't assume any particular distribution of the data, but it may be sensitive to outliers, as it scales the data to the same range regardless of their initial distribution. How to do min-max scaling? Simply by subtracting from the minimum value and dividing by the subtraction between the maximum and minimum. Min and max here are the minimum value of the vector and the maximum value of the vector respectively. The third technique is called robust scaling, and this technique is designed to be robust to outliers by using the median and interquartile range rather than the mean and standard deviation. So we are subtracting from the median instead of the mean and dividing by the interquartile range instead of the max minus minimum. The median is simply the first quartile. The interquartile is the subtraction between the third quartile and the first quartile. So if the data contains outliers, this method will be beneficial as it reduces their influence on the scaling process. and this will ensure that the features are scaled in a way that is more representative of the majority of the data. The last technique is called normalization, and this includes three categories of the normalization: L1 normalization, L2 normalization, and max normalization. For L1 normalization, we are scaling the data such that the sum of the absolute values of the features equals 1. And this can be useful for sparse data. Simply, we are getting the summation of the absolute values and put it in the denominator of the division. L2 normalization scales the data such that the sum of the squares of the features equals 1. And this makes this technique useful for data where the Euclidean distance is important. The last one is max normalization, and here we are simply scaling by the maximum value or the maximum absolute value, and this will ensure that the maximum value of each feature is 1. You may wonder that we discussed multiple normalization techniques: standardization, max norm, min max, max absolute, and so on. And you can ask that which method or which technique shall we use? Simply, it depends on the dataset and its distribution. But an easy way to overcome that challenge of getting statistics about each vector and the whole dataset for each dataset, simply you can make tuning and optimization. How? We have different techniques. Let's assume 5 techniques. We can try all of the 5 techniques and simply get the high performance one. So each of them will report a metric. By comparing all of the output metrics, we can say that technique is better than others for this dataset. And by getting, for us, let's assume min-max is better for this dataset, we cannot guarantee that min-max is better for all datasets. So it depends on the dataset and its distribution. Now let's assume the following example to understand how to calculate the different scaling techniques. We have a vector x here, 100, 200, -50, and 50. And we need to apply the max normalization. Max normalization is a division of each vector by the maximum of this vector. So the maximum value here is 200. So we will take each value here and divide it by 200. So 100 divided by 200 is 0.5. 200 divided by 200 is 1. -50 will be -0.25, and here positive 0.25. So the max normalization vector would be converted from this case to this case. What about standardization? It requires calculating the mean and standard deviation. The mean is the mean value of the vector. So by summing all of that and dividing by 4, because there are 4 elements in the vector, this will cancel each other. 200, 100 will be 300 divided by 4. So you have the mean. The same for the standard deviation. Then it will be 75 as the mean and 90.1388 for the standard deviation. Now you can subtract and divide to get the scaled vector. It will be this vector in this case. So if you summed this vector, you will get a 0 mean and a standard deviation of 1. So as mentioned, the standardization converts it to have a mean of 0 and a standard deviation of 1. Min max, we are subtracting from the minimum and dividing by the difference between max and min. So simply, the minimum here is -50, the maximum is 200. So here in this vector, plus 50, because minus minus will be 50. 200 minus minus 50 will be 250. And this will be the corresponding vector for the minimax technique. As you see, the minimum value will be 0, the maximum will be 1, other values will be between 0 and 1. The max absolute, dividing them simply by the maximum absolute value. So if the maximum value is positive, then max normalization and max absolute will be similar. So this will be the corresponding vector. By dividing by the absolute of 200 is 200. So this vector and this vector will be equal. The last one is the robust scaling by subtracting from the first quartile and dividing by the third quartile minus the first quartile, and this will produce the robust vector. As mentioned, we have different techniques and we can tune them and optimize based on the reported performance metric to get the best one or the best technique to be used with this dataset. After understanding the meaning of label encoding and scaling and the benefits behind each of them, the next step is to apply them before creating the model and learning it. And then you will need to create a new model or get a model and then fit or train that model using the training subset. And after training, you will need to test the model using the testing subset. There are different models, including traditional machine learning algorithms or advanced ones. Some of these models include support vector machine, key nearest neighbor, multi-layer perceptron, to test gradient descent, random forest, decision trees, ensemble models, and so on. The idea behind these models is that each of them has its own criteria of working and its own algorithm, but they share the idea of how to discriminate between the different categories or classes. So the simple idea is that we have two classes, for example here, and we need to create a boundary, or in a simple definition, something like a line that splits between these two classes. So if a new instance comes above that line, it will be related to that class. Otherwise, it will be related to that class. So the basic idea behind a machine learning classifier is that I need to create a pattern or a criteria or something that will be able to distinguish between the different instances. So when a new instance comes, it will say it's correlated or related to that category. We will not go in depth in describing each of these models, but we will know how to use these models from the scikit-learn library or any other libraries to be utilized in our framework so that we can teach that model to discriminate between the different categories and then test it, aiming to get a high performance model. So go to script 24, project 2, machine learning classification. We first imported the necessary libraries, OS for file and dictionary and directory operations, TQDM for progress bar and loops, and we imported pickle for saving and including Python objects, and we will describe the aim of it after a bit. Then we imported pandas for data manipulation and analysis. Then we imported our helper file. We first defined three variables: the base directory, where the data is located. Then we defined the dataset file that was created based on which feature we are going to extract. And then we are defining a variable where we are going to store the data and performance matrix that will be generated later. So this file should be in this directory. So if you are going to put this file in a different directory, then you need to update the base directory here. Then we created the storage folder path if it doesn't exist using make_dirs, and here we are creating the directory if it doesn't exist by passing storage folder path, and here we are joining the base directory, which is here, with the new folder name, which is here. So it will get the full path for the storage directory to be created. After that, we defined multiple scalars as strings, and then defined multiple models as also strings, and we will know the benefit of that after a bit. But here we defined min-max scalar, robust scalar, and so on. And here we defined multi-layer perceptron, random forest, adaptive posting, and so on. And if you need more classifiers, I will tell you how to add them in our code, and you can append them in this list. Then we created an empty list that will store the different metrics. After that, we created two loops, one for the models and another for the scalars, so that we will get all of the combinations between the model and the scalars. Then we created a try except block where we will try to execute that block, and if there is an error, instead of raising it, we will just print it and will handle the exception. And the aim behind that is simply because if you executed or run that iterations and before ending the loop, there is an error, then it will halt and destroy all of the experiment. So instead, simply, we will keep tracking of all of them. And once there is an error, it will be handled here, and it will continue to the next model and scalar, so that by the end we can benefit from getting the history so that we can store it later. What's inside these two loops? Simply, we created a function called machine learning classification version 1 that accepts the path for the dataset, the full path, using path join, the base directory, and the dataset file name, then passing the scalar name and model name as strings. This function returns three things: matrix, plot object, and objects. Let's focus first on the matrix. The matrix will include the different metrics, micro, macro, and weighted, alongside the true positive, true negative, and so on, and also the weights for the weighted matrix. Then you can uncomment this block and print the different metrics rounded to 4 decimal points. And the matrix here will be used at the end of this block to be appended to the history as a dictionary. This dictionary will include the model name as a string, scalar name as a string, the metrics, and here we are unpacking them to be listed as key values items. Then the second object is called plot object. Instead of letting this function to store and defining the paths and storage operations, we are going to return the plot object that contains the figure for the confusion matrix, and then we'll store it here. The benefit behind that is simply we are going to make any storage or any file manipulation in this area instead of inside each function. So this function will be dynamic for every application and it can be used with different datasets. Here we return the object, access the figure, and use the function save figure, and it will store the figure in the created folder using that pattern: model name underscore scalar name underscore CM. Then we will clear the confusion matrix and close the figure. What about this one? The objects here, as we are going to see what's inside it, will be stored as a pickle file. And a pickle file here can store different Python objects so that you can load it later to be used. So what's inside these objects? It's a dictionary that contains different objects. They are the model, the scalar, and the label encoder. Why we are going to store them? Because simply we are going to fit and train the model, and also we are going to train the label encoder, and the same for scalar. So we have now three objects that are ready and fitted on the data. So in a later phase, when we are going to test or have a new instance, instead of rerunning the experiment again and test the new instance, we are going to store that learned models or objects on our hard drive or disk so that we can later import it again or load it again and test the new instance. So here we are going to store them in a pickle file. So let's go to understand what's inside machine learning classification version 1 function. If you go to the helper file, you will find a function here that accepts multiple parameters: the dataset path, the scalar name, the model name, and three optional parameters. The first is test ratio, and here we are defining the test ratio, which is 20%. You can change it by simply pathing this value here like that, and also the target column, and this column is a string, and this should refer to the column that's inside the data set that refers to the classes or the categories. And in our data set, it's called class, so we'll keep that here. Or you can change it by passing the new value to the target column parameter. The last one is drop first column. If you remember that the first column stored in our data sets included the file name, and we mentioned that we need to ignore it and don't include it in our learning process. So if you are going to drop the first column inside this function, it will remove it. If you don't need it and removed it manually earlier, then you can simply change it and swap it to false and pass this value here. As you see, what's inside this function: first, we loaded the data using the read CSV file from pandas. Then we checked if you need to drop the first column. Then it checked that the first column is not equal to the target column, because sometimes you may put the first column to be your target, but it's recommended, as we did in our datasets, we kept the class name to be the last column. Then we will use the function drop on applied to the data with the first column name here, and it will remove the whole column using axis equals 1. Now we have the data without the first column. Then we will drop empty columns from the data frame, because sometimes you may find that some columns are empty. You will drop them to avoid any errors. Then we will drop any rows with null or empty values. Then we will extract the features and target. Why? Because these features, which will be called X, will be used to fit the model, and the target Y, which we are referring here to a variable Y, will include the column that includes the class names or the actual labels, and this will be used later to judge the performance by comparing the actual with the predicted columns. Then we created an encoder, and we mentioned the benefit of the label encoding by simply creating an encoder using the label encoder class and stored it in a variable LE, and use function called fit transform and passed Y. Here it will learn from Y what are the unique labels and the corresponding encoded values, and store the encoded vector in Y_enc, refers to Y encoded. Now we will use X and Y encoded in our process. We used a function called train test split, and this function is in the scikit-learn library that will accept our variables, and based on the testing size, it will return the training and testing subsets. Here, we are applying randomization to avoid any repeated patterns in the splitting, and use something called stratify. So what is stratify? Simply, if we have a data set with two labels, let's assume A and B, binary classification, A contains, let's say, 100, and B contains only 20 records, and we need to apply splitting with a percentage, 80% for training to 20% for testing, as we did in our example in the code. So if we took the whole records to the training test split without any stratifying, it may consider that the testing subset will include the 20 records from B and 76 from A, and this will be 80% of the dataset. And the rest, which will be 0 from class B and 24 from class A, as a testing subset. You may wonder that is this correct? Absolutely not. Because here it made a blind split, as a dataset here is imbalanced. So an issue that may arise from the train test split is that it can make a blind split and consider the splitting for the majority class, as it happened here. It only split it on class A for training and testing and kept only B for testing. But the benefit of letting the train test split to know that we need to apply stratifying is that it will ensure that this percentage will be applied to each class individually. So for class A that contains 100 records, it will be split individually to 80 to 20. So it will take 80% for training and 20% for testing. The same for class B that contains a minority instances that contains 20 records. It will be also split into 80 and 20. So it will take this 80 records and this 80% records into the training, and this 20 and this 20% for testing. So now we are ensuring that the 80 to 20 is applied to each class, and there is a balancing between training and testing. You can also ask, what's the issue if we used that? Simply, to let you understand the benefit, let's give another example. Let's assume again we have 100 for our training for class A and 20 for class B, and applying to train test split. Let's assume that the class B comes before class A in the ordering of our dataset, and we need to apply 80 to 20 again. So simply, the blind train test split may take 24 instances as a 20%. So it can take for the testing the whole P, which is 20, and only 4 from class A. And you will say, what about the training? It will take the rest for them, 0 from class B and 96 from class A. So if we took that subset and applied it to our model, it will learn, but it will say that any instance is class A because there are no instances for class B. So any instance that will be applied to that model will be categorized as A. So if you applied testing, it will give a very poor performance, while it will give, for example, 100 for the training performance. So there will be overfitting, and the model didn't learn anything to distinguish between the different patterns. So to avoid these issues, we need to let the model know that we are going to apply stratifying, especially if you are dealing with imbalanced datasets. So how to do so? We are going to tell the model to stratify according to the Y vector or the Y encoded vector. So it will treat each category as a special thing and split it according to that testing size. After that, we created a scalar. Then we fitted that scalar using the training subset and then transformed the testing subset according to the fitted scalar. So if you are going to use min-max, for example, it will learn first from the training subset and then transform the testing subset. Now we have training and testing to follow the defined scalar. After that, we created the model, and you may wonder, what are these functions? These functions will be found above this function, which are here and here. Get scalar object that accepts the scalar name and returns the corresponding scalar. For example, the min-max will import the min-max and return that object. For example, also, max absolute will import it from the scikit-learn package and return that object. The same for the machine learning classifier model object. It accepts the model name and the hyperparameters if it exists. Then, for example, let's assume we have a multi-layer perceptron. It will import it and return that classifier and unpack the different hyperparameters if it exists. There are multiple defined classifiers that can be used, and also you can add here any other classifier. For example, decision tree, it's here. Extra trees, it's here. Support vector machine, it's here, and so on. The same also for the scalar. If you have any other scalars, you can append it here as an else if statement. So the aim of these two functions is to get the scalar or the model name and return the corresponding object. And we made that to avoid any redundancy in our code. Now we got the model. We fitted it using the training X and the training Y. Now that model is trained, we can now predict using the testing. So we have the prediction and the actual. Using both of them, we can create the confusion matrix using the confusion matrix function from the scikit-learn package. We got CM. We will take that CM and pass it to calculate performance matrix and pass the absolute value. And we updated the calculate performance matrix to include one more parameter. This parameter, which will be found here with a default value by false, to come after each type like macro. It comes after the update to be checked. If it's true, it will get the average of the different metrics, and I will tell you what's the benefit behind this point after a while, and append it to our dictionary. The same for micro and the same for weighted. Here we will get the metrics, and this matrix will be returned as the first object. What about the second object? We created the confusion matrix display using the confusion matrix display function from the scikit-learn package, created the plot, defined the different configurations, created title and label, and adjusted the layout, then extracted the current figure object and returned it as a second object here. What about the objects dictionary? We created a dictionary to get the model, scalar, and the label encoder, and all of them are the trained ones or the trained objects. Now we have three things that will be returned here as we described from a while. So what is the benefit of the averaging that we applying in the performance metric? Let's say you have executed the code multiple times, one on first order, one on second order, GLCM, GLRLM, and GLCM, and now you have 4 experiments, which are unique and different from each other. If you executed the first order, you will get something like that, a folder that contains multiple figures that looks like that, and a CSV file. This CSV file will contain the different matrix alongside the model and the scalar name. We only reported here in this presentation the weighted matrix. So if you sorted them in a descending order, so you may wonder to get the best model or the best combination between the model and scalar, you may ask which metric we are going to sort according to it, whether it's accuracy, F1, or recall. So as a simple idea or as a simple trick, you can simply get the average of these metrics. So if you have 5 metrics, you can add them together and divide by 5, you will get the average metric. And this is what we added in our performance measurement. So you can sort descendingly from here according to the weighted average. By doing so, moreover, this weighted average will be a weighted metric that combines a ratio from each metric. So this value here or here will be a value that considers each other metric like specificity, recall, and precision. So if you sort it, you will find that in our experiment here, that the extra trees with the standard scalar got 82.24. And this is the corresponding confusion matrix. And it's multi-class classification because we have 4 classes. This is the true, this is the predicted. So from it, you can extract true positive, true negative, and so on. And it worth noting that if you run the experiment on your computer, you may get different results because some algorithms depend on randomization. And we also applied randomization in the training testing split. But you should get a performance that's close to these results. So you may get, instead of 82, you may get 83 or 84 or 81 as the highest performance. And as a trick or as a behavior to this randomization and to overcome this issue, you may run the experiments multiple times, for example 5 or 10 times, and get the average and standard deviation for each metric. But as a current step here, we will only run the experiment one time just for illustration. What about the GLCM? GLCM reported that the multi-layer perceptron with the robust scalar reported 85.24, which is higher than the first order features. This means that using robust with MLP are able to discriminate better between the different categories. But when we apply GLRLM, the performance dropped than the GLCM and first order. It reported 78.88. And for GLSCM, it reported 80.25, also for the MLP and robust scalar. If we combined as a summary table the different feature types, first order feature, GLCM, GLRLM, and GLSCM, with the top one model and scalar for each experiment, we will find that GLCM reported the best of them, 85.84 as a weighted average, and as an accuracy 89.66, and as a recall 82.24. So we can now consider that in this experiment and this data set, the GLCM features are better than others. Now you may ask that why we didn't combine the different features together as we mentioned at the beginning of the lecture, such as combining first order and GLCM. I can tell you, you can do that by simply turning on the flags for FOF or the first order features and GLCM to be true and others to be false, or whether combination you need to do. Or simply, there is another trick. If you extracted the features individually like what we did here, you can go to the data, first order features or GLCM. Let's combine these two. So I will copy this one, and we need first order features and GLCM. So I will add dash here, GLCM, open that file. For sure, it will include the first order features only. So open also the second one, which is the GLCM that's required to be appended or added to our feature list. And take the features from the second to the last and copy them. Go to the last column and right click and select insert copied cells. It will insert the cells at the end, but before the classifier. Double check two things if you did that. First, the number of records match together here and here. And for the combined features, compare the files together randomly. So I will take this column from the GLCM and insert it here, and we need to compare them randomly to ensure that each record matches the other. So let's scroll down, take that one, it's 1158, 1158, scroll down, 18, 1291, 1291, scroll down, let's scroll down with 10K, 1756, 1756, let's scroll down again, 8427, 8427, and the end looks like that. So they are matching. Now you can remove that column again using right click and delete. Now you have first column that includes the file name, the different features, and the category at the end. Save that and close. Now you have the features for first order features and GLCM combined together. You can now comment this and add a new experiment, but now with first order features and GLCM. So I will update this name and update this folder name. Now you can run the experiment, Python 24, project 2 machine learning classification, and it started the experiment for the models and scalars. And once it completes the execution, you can compare the result with our reported results in the presentation and check whether combining first order features and GLCM is better or getting better performance than working individually on each feature or not. Now, after completing the execution of the code, it will give you a completion statement. And if you want to the corresponding folder, which ends with first order feature, GLCM features, you will find different outputs. Let's change the display and sort by type. You will find the pickle files here named using the defined pattern, and similarly the corresponding confusion matrices. If you opened any of them, you will find the corresponding confusion matrix for decision tree and the QT scalar. And if you need all of the metrics, you can refer to the history, open it. You will find the different performance for the different combinations between the model and the scalar. It begins with the components, then macro metrics, then micro, and the weights, and ends with the weighted average matrix. So let's assume we need only these scores. So for now, let's delete these columns. So right click and delete. So now we have these metrics. You can format it as a percentage, format cells, and select percentage. As you see here, you can center the content and align it in the middle. And also you can format it by auto fit column width. Also, you can select the data and add a border as you see here for a good display. Now, if you need to sort according to the weighted average, you can select the editing panel and sort from largest to smallest. Expand the selection and sort. You will find that performance for the MLP and robust got 86.63, which is higher than the reported metrics using the GLCM alone. So combining the first order and GLCM reports better performance by 1 or more percentage. You can also combine different combinations between them, or you can combine all of them together to check the performance. So for now, our best model using first order features and GLCM combined is MLP model and robust scalar. Remember these two names for now, and we will return to them after a bit. Now we have trained the model. Let's assume we have a model here named M. The aim of training the model is to get a high performance model. Let's assume for our experiments it's around 86. And we are for now accepting that model and stored that model as a pickle file alongside the scalar and the label encoder. What's next? We need to apply testing. And the aim for testing or using the stored model is simply if you have a new image which is not included in our dataset, for example, and we need to check that image, whether it's COVID or null opacity or luminia or normal, then simply we need first to get that image and apply feature extraction using the two defined features, first order features and GLCM, combine them using the same pattern that we followed during concatenating these two features types. Then take that record and apply it to the model to get the output, which will be one of the 4 classes. So let's assume we have a record. And for now, let's pick it randomly from our dataset. And we need to know how to load the model and test that fit model. So simply go to code 25 project 2 machine learning testing. We imported the same packages and imported also NumPy. Then we defined the same paths for our feature list and the storage folder. Then we mentioned from a while that we need to remember these 2 names because we will load only the best model, which is MLP and robust. So go to here, best model and best scalar, and update them. We have MLP and robust. Define the category column name and drop first column, similar to what we did in the training process. Here it's class and we need to drop the first column, so it's true. We define the pickle path. It's included in that folder, inside that folder with that pattern, best model and best scalar with underscore between them and .p for pickle file. After that, we loaded that pickle, which is the objects dictionary. We accessed to get the model scalar label encoder, loaded the data set and got a random instance from it, then got X and Y, which refers to that random record. If you need to drop the first column, get only the features, then scale it using the transform function from the loaded scalar, which is here. We didn't create a new scalar, but we loaded the stored one and used the transform function to transform X to the scaled X, then used that to apply it to our model, which is in the variable model, and loaded also from here and got the prediction. The prediction will be encoded from 0 to 3, but we need the actual name from it. So we can use the label encoder, which is loaded here, and use the function inverse transform. By passing the prediction, it will get the corresponding name back. So for example, if it's 0, it will be normal. If it's 1, it will be Luminia, and so on. Then we printed the outputs, the random index, the selected random index, the feature vector, and the actual label and the predicted label. And both of them will be as a text. So if we execute the code, it will get a random index, the features vector, and here it says that the actual is normal and the prediction is also normal. And this means that the predicted equals to the actual. In real world cases, we will not have the target or the reference, but we will only get the prediction based on the features concatenated together. And this is another example. The features using that random index, and the output is lang opacity, and the actual is also lang opacity, and they match together. So in this lecture, we covered many things. First, we mentioned how to acquire the dataset and described the utilize dataset in our experiments and the lecture. Then we went through the different steps from extracting the features and storing them into CSV files from the utilized dataset for COVID-19. And based on the extracted features, for example, here we extracted first order, GLCM, and so on, we utilize these extracted features into our model or classification process. The classification process included label encoding to convert the actual tags or labels into values, numerical values, and then applied scaling. And scaling here is to unify the ranges for different features vectors. And after that, we applied the model by creating it and teaching that model to discriminate between the different categories. And we also know how to calculate the performance for binary and multi-class classification. And by the end of this lecture, we understood how to load the best model and test it on a random sample.